All right, guys, so this is for 22 to 38. So a lot of these equations are kind of, I wouldn't say the same, but it's the same process. You just have to get good at identifying them and plugging them into the right equation. They're not that hard, though. Okay, but I'm just going to show you either way. Now we're working with forces and acceleration. You did a little bit of accelerated motion in the first 21 questions, but let's go ahead and just get this underway. So this right here is force, right, because you see newtons. Has a mass of that, so blah, blah. And what is the acceleration? Okay, so we need an equation that has force, mass, and acceleration, so I'm going to look here. And let's see. No, that's acceleration, velocity, no good, no good. Oh, here we go, net force, mass, and acceleration. How about that? So I'm going to use that one. So F equals ma. It's not like the traditional equation we've been using, but whatever. At this point, we're just going to go ahead and use it because this is what we're going to use on the night. Okay, so we're looking for acceleration. So we got to rearrange that equation. Force equals mass times acceleration. How do I solve for acceleration? I got a check mark on these. I just divide mass on both sides, right? So force net over mass equals acceleration. You make sure to show the step, or at least write this equation here so you already have it on your formula chart. That's fine with me. Okay, so you get 419. Show this step, 419.4 over mass of 264.9, and that's going to end up equaling your acceleration there. All right, so let's go ahead. I'm going to erase some of that stuff. That's be gross. Let's get rid of that. Cool. All right, great. Okay, I'm going to do the next one as well, just to kind of like help with this a little bit. Okay, it's kicked with that. Actually, I'm not going to do this one. Okay, you set it up the exact same way. So this is force. Acceleration, what is the mass of the ball? So it's the same equation, just I'm rearranging for m this time, okay? Make sure you show your guess method. So your givens are force equals 12.5 newtons. You also have, what else? Acceleration is 6.9 meters per second squared. And your unknown is the mass, okay? So your equation, you're going to pick one of them from up here, and you're good, okay? Okay, let's move on a little bit. Okay, then I have here 24. This is a very simple one. This is Newton's third law. So what's Newton's third? Everything has an equal and opposite reaction pair. So look, if it's 890 gravitational force on the man also exerts gravitationally, not with normal force, but the exact same gravitational force. It has to be the exact same. Don't forget about that. They're all the same. So look at this next question here. The exact same thing. Look, 27, 32 miles up in the air. This is that trippy fact I taught you earlier this year, that it's always going to be the same. But because, what is the difference that we see then? It's not a difference in force, but we obviously see if I drop something. So if I have, like, here's the surface of the earth, and here's you as a man or whatever. You notice that, like, you see the red dot falling really quickly. But the earth is actually also being pulled up, but at a much slower rate. So that's the difference you see. You have the same forces, but because the mass of this guy down here is so much greater than this guy, you see a much greater rate of change of speed. Okay, cool. All right, let's go ahead and move on. I'm going to go to 29. That's going to be on the next page. All right, so here's 29. Let's blow it up. All blowed up. Great. Initial acceleration of blah, blah, blah. So that's my acceleration. How long? So what type of question is a how long question? How long is a time, right? To bring the bicycle to an initial speed with an initial speed of that. So initial means v initial, right? To a complete stop. Okay, what's the secret that's given here without needing to be told? A stop means you're not moving. Moving is velocity, right? So v final equals 0. That's important right there. You need to make sure you get that there. Let me blow this up a little bit more. All right. Okay. So I'm looking for a how long based on acceleration, v initial, v final, and time. Okay. So I'm looking for time based on that. Let's see. Let's look at our equations here. So what equation has acceleration? Final velocity, initial velocity, and time. That one. Okay, I got these, and I'm looking for that. So this looks like it's going to work, right? Because I'm only missing the time, right? Okay, so let's go ahead and use that equation. All right, sorry. All right, so you have that on your star chart. Just go ahead and refer to it. This is what you're going to have the entire time. So acceleration is change in v over change in t. And which one am I looking for? This guy right here, right? So what do I do when I have a top and a bottom algebraically? I can switch these out, right? So you have change in t equals your change in v over a. So let's get my change in v. What's my change in v? V final minus v initial. What was my v final? At the end, I'm coming to a stop, so my final is 0, right? So that's 0 minus, what's my v initial? 13.3. Notice this top side is going to become negative, but that's okay because look at my acceleration. What was my acceleration at the beginning? My acceleration was negative 0.56, so that's going to end up being positive, negative 0.56, and that's how you end up with a positive time interval there. Okay, cool. Not too bad, right? Okay, let's get rid of all this crap. All right, the next one I had slated for you guys to do was 31. So the rest of these are just kind of representative of all the same crap. So like, don't freak out that I'm not working out every single one of them. They're all kind of the same idea, just guess method. Can't find it. 31. Okay, it's up here. No, it's not. The hell did it go? Oh, here we go. All right. Ball rolls down a hill, then acceleration. Oh, what happened to my formula chart? Where did it go? There it is. Come down. There we go. Okay, ball rolls down a hill with an acceleration of blah, blah, blah. So that's my A. Accelerates for that. That's my change in T. How far is a displacement change in X? Will it move? Okay, so remember the other symbol for that is that, right? Okay. It's initially at rest, so that's my secret given right there. We practiced these earlier in the year. So what do I do for my givens there? I have change in time equals this guy, 7.8. I have my acceleration, 2.6. What else do I have? My initial velocity was a secret given. That's 0. And we're missing also final velocity, but I may be able to do some stuff without that, right? I may be able to do some stuff without that. So let's see. My unknown is my change in x or my displacement. So let's look at our formula chart and see if we can do some stuff with just the information given. If I can't, then I'm going to have to do some other things. Okay, so displacement. Let's see. I only have one thing with displacement right away, right? Hey, see you later. Okay, so if you look really carefully with my blue lightsaber here, you can see that this one would be no good. Why is that? Because I got final velocity. I'd have to find final velocity, subtract initial velocity, and then my change in time, but I still wouldn't even be getting a displacement that way, so this isn't the first place I want to look. I can't use this one because even though I have velocity, it's average velocity. So this is, I have an initial velocity, I don't have average, okay? The displacement would be good and time is there, but again, this isn't right because I have to take into account the fact that I'm accelerating, right? It's not the same as moving at a constant speed. But look here, here's a displacement equation. I have initial v, which I do have. I have change in time, 1/2 acceleration, which was given, and then my change in time again squared. Okay, so that's this equation right here, and we use this a lot in free fall. So let's go ahead and use this guy. This is the one you're going to want to use for this one. Okay, so let's get this out of here. Okay. So that's displacement equals velocity initial times time plus 1/2 at squared. Okay, now my initial velocity is 0, so I don't need to worry about that. So really I'm just adding 1/2 at squared. All right, so it's 1/2 times my acceleration, 2.6, my time squared, which was 7.8 squared, and then that's going to get you your answer like that, okay? Erase this so I have some space. Okay, after that I had 34, because the rest of them are just plug and chug those same types of problems. Okay, so let's go over here, okay, 34. Okay, notice the type of graph I'm looking at in this video is not displacement time, but it's velocity versus time, right? Okay, so think about it before when we had displacement versus time, the slope of that one was the velocity. Now the slope of velocity is going to be, let's look at our formula chart and see what the slope of velocity is. Well, look, if I get the change in velocity over the change in t, like my x and y-axis, so you notice this was my y-axis, so this is my change in y, this is my change in the x, right? And look what it equals. It equals acceleration on this graph, right? So on this one, you're going to be able to figure out your acceleration based on the slope of this graph. Okay, that's very important. You need to know that. So if they ask how fast or what is the rate of acceleration just by looking at this graph, well, I don't have acceleration on this graph, but I kind of do, right, if you think about it. So where am I not accelerating? I'm not accelerating from 2 seconds to 6 seconds because I don't have a slope that is not zero, right? The slope here is 0, which means I'm not accelerating. My change in y is 0, and that's change in velocity of 0, right? Okay, what is the acceleration at 1 second? So go to 1 second. It's again, I'm looking for the slope through that point right there. Through that point right here. Okay, so how do I find the slope of that? Well, let's see. I'm going to go ahead and take this point and make the slope from there. So my change in y over change in x, it looks like I go up 1, 2, 3. This is plus 3 over my run. And I have to make sure, be very careful, you're counting. It is counting by ones, okay? This is 3 over 2. So that's 1.5. You can put that in the calculator, 1.5 meter per second squared. If you're going the equation route, you're going to use this equation right here. Final minus initial over the change in t. So let's go ahead and try that. So again, this is just like doing a word problem, but I'm picking the information off of a graph instead of out of a paragraph. So my final v final, v initial, this is my t final, and this is my t initial. Right? Just like I do the guess method, I can do the guess method on a graph too. Okay, so my v final, 3 minus 0 is my initial, over 2 minus, and this actually wasn't my initial time, this is my initial time, sorry. Okay, so that's 3 over 2, so same answer either way, right? And it's positive because look at the slope, it's a plus 3, not a minus 3. All right, cool on that? Not too hard, right? Okay. From there, I had 35, 36, so I'm just going to basically show you how to do this graph a little bit more. What's the velocity at 2 seconds? Oh, come on. What's the y-axis charting? The y-axis is charting velocity. Just go to 2 seconds. What's my velocity there? Okay, come on now. All right, and what is the position at 2 seconds? All right, these are a little harder because this is when we had to do the area, okay? Because v times t, if I look at my graph, so if I look at velocity, v times t, or if I look at displacement, which is kind of the change in position, right? It's initial velocity times time plus 1/2 at squared. This is that thing where we made rectangles. So this was a big rectangle, and this was a triangle, right? So this was the area of a rectangle, area of a triangle type problems, right? So this is how we're going to do it. You ready? Okay, position at 2 seconds. So these are kind of tough, but they're not that bad. 2 seconds is here, so what shape do I have? I have a triangle, right? I have a triangle. Okay, so my base of the triangle is 2, because it goes from 0 to 2. My height is 3, so what is the area of a triangle equation? 1/2 base times height, and that's going to be 1/2 times 2 times 3, which is 6, so it's 3. But that's not my answer. My answer is not 3 meters because what was my starting position? 10, right? So my position is going to be 13 meters. So be very careful with that. Okay, if you go the equation route, it's kind of a pain in the butt, but it's not the worst thing in the world. Let's see. So if we go the equation route, we got to do initial velocity, which was what, 0, times the change in time, which is 2 seconds, plus 1/2, and look, this is going to be kind of interesting, right? The acceleration, which we had earlier, was 1.5 times the time squared, which was 2 squared, right? Sorry about that, let me redo that so it's not confusing looking. Okay, so 0 times 2 goes away. So you have 1/2, 1.5 times 4. And if I put that bad boy in the calculator, 1.5 times 4 is 6, right? And then divided by 2, guess what? You get the exact same answer. 3 meters is the displacement during that time interval, but you have to add it to your initial position, right? So you get 13 meters again. Either way, it's like the guess method, but you're using a graph. Really cool stuff, right? Okay. Let's see. I think that's all I had for this one. Yep, that's it. All right, good luck with that. This should get you more than halfway through the entire midterm review. That's pretty snazzy, right? Good luck.